All right, welcome back. We're going to continue our discussion on motion. So at the end of this chapter, these are all the things that we'll be able to cover. So far we've already looked at explaining how distance, position, and displacement are different. We've talked about vectors and scalars, scalars having magnitude, and vectors having magnitude and direction. Okay. Today's goal, we should be able to explain how speed and velocity are different, and we'll chat a little bit about acceleration. So section 1.2 for us is average speed and velocity. Average speed is the total distance traveled divided by the total time taken to travel that distance. So now distance, you'll remember, is a scalar. Okay, and if we take that scalar and divide it by time, which is another scalar, then our result will be a scalar. Okay, so speed, or average speed, is going to end up being a scalar quantity. So if we scroll down here, and if you take a look at the formulas for 1 second, you'll notice it's the change in distance over the change in time. d2 minus d1, you might recognize this as being the slope formula from grade 9, which is a rate of change, which makes sense. So if we have something like example 1 here, a dog travels 54 meters in 9 seconds. What is the dog's average speed? So if we looked at our average, we would have 54 meters traveled in 9 seconds, which means he's traveling at 6 meters per second as an average. Okay, and again, that doesn't mean that every point or at every moment in time he was traveling that exact speed. It means it's the average. He probably started off a bit slower, got really fast, and then slowed down near the end. But what we find is the average speed over that interval would be 6 meters per second. Okay, so let's take a look down here. We have a sprinter. Our sprinter is 8 meters from the start line. 1.8 seconds into the race. At 8.3 seconds, the sprinter is 72 meters from the start line. What is the sprinter's average speed? So if we look at this, we need to see the change in the distance traveled. So we have 72 meters minus 8 meters. And we have this occurred at 8.3 seconds, and this occurred at 1.8 seconds. So this is the change in their distance, this is the change in their time, and if we do a quick calculation on that, assuming I can find my calculator, 72 minus 8 is 64 meters. 8.3 minus 1.8, 7.3, 6.5, and that's pretty close to 10, but let's just double check. 9.85, we'll say. Oh, we better not. Let's do 9.9. It's safer. Meters per second, approximately 10 meters per second. How fast would the sprinter run the 100-meter dash? We're looking at, now this is that same sort of relationship, only in reverse. We know that their velocity is 9.9. We know they're traveling at a distance of 100 meters, and we want to solve for t. So if we rearrange and divide, we can do 100 divided by 9.9. That's about 10.1 seconds, which is incredibly fast. Approximately. So that's world record kind of area. If you're that quick, you better sign up for sprinting. Okay, next one. Average velocity. Well, average speed was a scalar. Average velocity, you could probably guess, is going to be a vector. So average velocity is the total displacement, which is a vector quantity, divided by the total time. Okay, and now you can divide a vector by a scalar. The result is still a vector quantity. So a vector, or a velocity, is a vector quantity. You'll notice the formulas are almost identical. The only thing slightly different is this little arrow above the V's, the D's. There shouldn't be one on the T because it's not a vector quantity. Okay, that shouldn't be there. And that's how we denote a vector. And We won't get too bogged down in those little pieces. We just need to know that speed and velocity, one is a scalar, one is a vector, and we'll leave some of those little details in the formulas for your higher level maths. Both of them, though, are rates of change, which are slopes. That's going back to grade 9. So your average speed and average velocity are examples of rates of change. Okay, and that shows up in a lot of the different problems. It's going to be with us for the next few weeks for sure. And it is the change of position over change in time. And that's the heart and soul of it. And that leads to something called a position time graph. So a position time graph describes the motion of an object. Okay, so if we have a chance in class, we definitely model this. But we'll try one here just on paper or on the screen, and then we'll see if we have time to insert a video or do a live demonstration of some of this. So we have two soapbox racing cars. They're non-motorized cars. They're normally perched on a hill and then they're released. They're in a race down a hill. However, car A has been given a 10-meter head start from car B. Determine the average velocity of each car. So average velocity of each car. So this will be a displacement question. So if we look at car A, I have a table of values with its position and the time values that go with that. Now you can see all of these ones here. These are changing by 1. We have a change in position of 4 meters here. So our average velocity here would be 4 meters over 1 second. Okay, now if we take this second grouping, this is a change of 3 seconds. This is a change of 12 meters. And if we did the average with those, we would have 12 over 3, and it's still 4 meters per second. Okay, so if we look at our graph, car A had the 10-meter head start, so it starts here. And you can see that's a linear relationship. That shouldn't be a big surprise from grade 9 math, because the rate of change here is constant, the first differences are constant, it plots linearly. Car B, and we'll change to red for car B. Give ourselves a little bit more space. Okay, now for car B to catch car A, it has to be traveling faster than 4 meters per second. Okay, otherwise it'll never catch up to it. So if we take a look, I'm going to take a look at the interval between 1 and 2 seconds. Okay, so if I looked at my rate of change between 1 and 2 seconds, I would have 6 meters for every 1 second. So that makes sense that it's going faster. If I look at another interval, this is changing by 2 seconds. This is changing by 12 meters. So my rate of change down here, I should call that V for velocity, my apologies. And lo and behold, I get the same 6 meters per second, which makes sense because, as we said, this is a linear relationship here. We're going to just connect these guys. And we can see at this location right here, because this is a position time graph, okay, this position right here, both cars are at the same position. That means car B has caught car A right here, and that happens at 5 seconds into the race. Okay, and you could also see that over here in the table of values. Now, actually, I should go back and look at 1 or 2 other things here just to point them out. You will notice that the rate of change, the velocity of that red line, was 6 meters per second, whereas this guy up here is 4 meters per second. And those are both rates of changes or slopes. Okay, because 6 is greater than 4, it's also steeper. Okay, so one of the things we're going to connect in the future with our position time graphs is we'll also be looking at slopes and the rates of change and how they tie in with velocities. Okay, so motion with uniform or constant velocity is motion at a constant speed in a straight line. Okay, it's our simplest type of motion that an object can undergo. You've probably encountered it in other science classes or math classes before. but just in case you haven't, let's just go over it really quick. So we have this little formula off to the right-hand side here. Velocity or speed, you could actually interchange it in this question, equals distance over time, displacements over time, some change in position over time. This is a very popular little equation. Okay? What it means though is there's no acceleration. That's a really important concept, and we'll spend more time talking about what acceleration is. That means that the velocity or speed will be constant throughout the entire problem. Non-uniform velocity is motion that's not at a constant speed. It's not in a straight line. And so it could be accelerated motion or motion that's happening in a curve. Okay, so just a quick check-in. A car travels down a straight highway at a steady 100 kilometers an hour. That's uniform velocity because it's straight line and it's constant velocity. A passenger on an amusement park ride travels in a circle. As soon as you see circle, you're into non-uniform, and we'll do more on that in grade 12. A parachute jumps out of an aircraft. Now this is tricky because there are times where it's constant after the chute opens, but before it's non-uniform. Okay, so it has a little bit of both. If you've ever ridden in an elevator, when the elevator is rising or going downward, either one, it feels, you have a hard time even knowing you're moving because you're traveling at a constant velocity or speed. The only time you know when the elevator is actually moving is usually when it starts or when it stops. There's a bit of a lurch. Okay, and that would have non-uniform velocity at both the start and end, but the middle travel should be uniform. If there's time, I'll insert a video here. If not, I'll normally do this live. I get you up and running with using something called a CBR. We'll see how that works. If we don't get it in though, this is the types of motion. So we have position time graphs here and a quick summary. So object starts 5 meters from the reference point. Maybe I can do this and just make it a little less visually burdening. Okay, so the position does not change. So over here you'll notice that position line is not changing. The object is a consistent 5 meters away from the reference point. This object is not moving. Okay, the other thing we can look at is what is the slope of that line? Well, the slope or the rate of change is 0. Okay, so it's not moving. If we look at this next one here in blue, the object starts at 0 meters from the reference point. The position is changing now because what we start to see is this position in here, these values are getting bigger. And because they're getting bigger, that means the object is moving away from the reference point. Okay, so this object is definitely moving. If we look at the slope or the rate of change of how that's moving, we could see that that is 5 meters traveled in 5 seconds, and we would come up with 1 meter per second as that object's average velocity or average speed. Okay, and then we'll finish with the third one here. Object starts 10 meters from the reference point, so that's this location right here. Position is changing over time. Okay, so we can see these values here are getting smaller and smaller and smaller. Okay, so the object is definitely moving, and in this case it's moving toward or back towards the reference point. Okay, because that position value is getting smaller and smaller and smaller. If we look at the slope or the rate of change, okay, again, now we have to be very careful in here. We can't just use this 10 meters. That's incorrect. We need to look at this change. So there's a change in position of negative 5 meters. It's gone down from 10 down to 5, and that happens over 5 seconds. And we end up with negative 1 meter per second, which is that slope there. Okay, so this is a recap from your textbook. You can look these up. They're talking about position, and they have the ability to go below 0. So you'll look at the first one here. This object is not moving, but it is to, in this case, it could be to the left or in the positive side of the reference position. Down here, this object is not moving as well, but it's to the right or to the negative side of the object that is our reference point. That's the only difference, okay? But neither object is moving. It's just giving you the relative location based on the reference point. Okay, these objects are definitely moving. So this one here, again, is a moving away. Okay, this one is moving away, but quicker because the slope or the steepness of the blue line is greater. Okay, so it's away and faster, if you want to think of it that way. And you can read all of these little points or bullets. They're in your textbook. This one is moving back toward the reference point, and it's moving quicker than the first one, but it looks like it's about the same as graph D or the second one. Okay, so on page 20, got questions 4 to 7. You could give those a try. Thanks for tuning in.